All right, so today we're going to continue graphing polynomial functions, and I pulled up Desmos to graph a few functions so that we can explore this intercept form that we left off with last time. So this first one, we have a degree 2 polynomial, and we notice that we have x-intercepts at -1 and +2. We can see that easily in our intercept form. What I wanted to explore today is to see what would happen if our polynomial has exponents in a portion of its factors in intercept form. So I have different polynomials here with different exponents. So let's go ahead and just start graphing them to see what happens. So this first one, we notice that we now become a degree 3 polynomial. So we have a shape of a cubic, and our intercepts are still the same, -1 and 2. One thing I notice is that we have this intercept happening at -1. And if we zoom in, we notice that we're actually not crossing the x-axis anymore. So in contrast to what we had in our original function, we had a traditional intersection between the function and the x-axis. Here, we are just bouncing off the x-axis at that point. So if we look to the third power, now we see at -1, we have this little kink in our function. So it flattens out for a moment, and then it crosses at -1, and then it continues going. So here we are actually crossing, not like the bouncing off of our last function. And so let's keep exploring to the fourth power. And oh, look at that as another bouncing off point. So let's kind of compare those evens back to back. Those even exponents, we change colors there. And we notice that the end behavior is very similar. The intercept x-intercept is very similar in those two functions. We have this bouncing off point. I'm going to go ahead and graph all the ones that are even to see if we can make a conclusion. Ooh, so we notice the end behavior again is not changing. So we are still increasing in either direction. And we notice this loop is getting longer as the exponent increases. But what I'm really concerned with is how the x-intercepts are all very similar. So here at 2, where we didn't change anything, it's still a traditional intercept. And here it bounces off when we have an even exponent. Let's go ahead and see if there's something we can notice with the odds. I'm going to click on all these odd ones. There we go. And similarly, all of the zeros that have an odd exponent interact with that -1 in the same way. So we have this point of intersection at -1, even though it flattens out, it only crosses at that point. So multiplicity happens when there is multiple roots at the same point. So we can have two options. We can have an even exponent or an odd exponent. We notice the even exponent has this kind of tangent line. So we can call this point of tangency. So tangency means that we are touching the line, but we do not cross it. And I also like to think of that as a point where we bounce off the x-axis. So we do not cross it. What that looks like here, we have this point of tangency. So we can see we're not crossing the x-axis. And we do have a traditional interception here. And we can tell when we have that multiplicity, when we have an exponent that is even. So we would indicate that when we find our zeros by saying this has a multiplicity of 2. Has a multiplicity of 2 because the exponent is 2. Our other zero is just a regular old 0 at x equals 2. For an odd exponent, we noticed that we have this kind of kink in the function. It becomes a turning point at that x-intercept. So I'll put like a kink here in our function. And we can tell on our polynomial that we have a kink because we have an exponent that is odd. So at x equals -1, we now have a multiplicity of 3. And here we have a regular old x-intercept of 2. So what this multiplicity means again is that we have multiple x-intercepts or zeros happening at the same point. So here we have 2 zeros at the same point. Here we have 3 zeros at the same point as well. I'll go ahead and mark that on our graph. We have this kink in our function here, and then we have a regular x-intercept at x equals 2. So when we begin graphing or we begin writing our equations, it's really important that we can notice these details so that we can either graph them correctly or we can make sure they are communicated correctly in our polynomial function. Let's go ahead and look at graphing these polynomials. And when we are graphing, there's a couple things we want to notice before we even start going to the coordinate plane. The first thing we always want to look at is the degree of our function. And the degree will be our highest exponent. So here we are in intercept form. So I want to make sure I'm multiplying this out to find the degree. So this would become an x squared times an x would be x cubed times another x would be x to the 4th power. So this would be a degree of 4. And I notice that I have a leading coefficient of -1. What does that mean? So when I have a negative leading coefficient that has an even degree, I know the end behavior is going to be very similar to a downward facing parabola. So when I'm graphing this, I want to make sure I'm starting down here and I'm ending down here. So the end behavior has to be the same. The next thing we want to notice is our zeros. So let's go ahead and find those zeros from intercept form. So I have x equals 0 here. I have x equals 2 with a multiplicity of 2 zeros occurring at x equals 2. And then I have another 0 occurring at -1. Remember, we're finding these zeros that turn each factor into 0. The next thing I will do is go ahead and plot those points on my coordinate plane. And I'm going to highlight this one that has the multiplicity, just so I don't forget what I'm doing with that point. So when I draw my line, I need to tend to my end behavior. So again, we're starting down here at -infinity. And we're going to end down here at -infinity for our function, our y values. So I'm going to go ahead and go through -1, have this kind of turning point, this peak back through 0, and then I need to bounce off 2 and end down here at -infinity. So I'm going to go increasing up through -1, down through 0, and then I have to have this point of tangency bouncing off 2. So it's not the most accurate sketch, but it gives us a good idea of our shape for this polynomial function. Another way we describe our polynomial functions is with maximum and minimum values. There are 2 ways we describe max and min values. We can have a maximum that is what we call a global maximum, or also known as an absolute maximum. These 2 terms mean the exact same thing. It's up to you which one you would like to use. So they mean both the same. So what these 2 words mean is that the function never takes on a greater value. So this is what we would think of as a traditional absolute maximum. Now we can have what we call a local or a relative maximum. And that just means like on a specific interval, that would be the greatest value. So the function does take on a greater value somewhere else. And we would just consider these to be a local or relative maximum. We can also describe minimums in the same way. A minimum could be global / absolute, or we could also have a local or relative minimum. So I have 2 functions here, and we're going to go ahead and look at we're going to look at what a local or a relative min or max looks like and what a global or absolute min or max looks like. So the first thing I want to notice is that we have these things called turning points where our function is changing directions. And that's another good thing to notice. So I'm going to write that down. We have 2 turning points, and I'm going to call those TPs here in the future, so we don't have to write down as many words. And I am going to notice that here I have a minimum, and here I don't have anything. I'm going to erase that. I just have a kink in my function. There's no min, there's no max at that point. Just kind of changes direction. So here I can see I have an absolute minimum, because you'll notice that if we take this min and we go to the y-axis, there is no function value that is less than that value. This is the very smallest point on our function. So absolute means it's the only value, it is the smallest of all values. So we have no maximums here because this is going to infinity, so we don't consider that to be a max. Let's look at our second one. We have, let's see, 1, 2 turning points, so 2 TPs. And I see we have a max here and we have a min here. So they may not be an absolute max and min. And I can tell because if I kind of look at the rest of my function, I can see that there are places where the function is greater and there are places where the function is less. So this is what we would call a local or a relative minimum and maximum. So this would be a relative minimum and this would be a relative maximum. So along this specific interval, this we would consider as the maximum value. I have 2 more examples that we'll just kind of look at together. So here we have one relative max, we have a relative min, and then we have an absolute minimum with 3 turning points. And we have another one here where we have one relative maximum, and then we have this place that the 2 minimums are actually the same value. So we have one absolute minimum, but it just occurs twice in those 2 different intervals. All right, and lastly, the thing that we will practice is how to write a possible polynomial for a graph. So just like we do when we're graphing, we're going to take some of those key features and then use what we know about polynomials to write them into an equation. So you'll notice that they direct you to use a cubic function. So we'll do a cubic or quartic, which means in the cubic case, we have a degree of 3. So that means we have like x to the 3rd, right? It's going to be our highest power. The next thing that they tell us is that we are using our x-intercepts. And we are also deciding whether we have a positive or negative leading coefficient. So we already noticed that our degree is 3. So I need to look at the end behavior. So I notice my function is increasing. And this would be an odd degree. So it will behave like my traditional cubic function. And because the end behavior of this function matches the end behavior of my traditional cubic, I know that the leading coefficient has to be positive. So I'm going to use, oops, that's not positive. Circled the wrong one. There we go. We're going to use 1 as our leading coefficient. So I know the degree and I know the leading coefficient. The next thing I need to know are my intercepts. So I have an x-intercept here at -2, an x-intercept at 0, and an x-intercept at 3. So these are the zeros. Now I need to take these and write them as factors. So here is my polynomial. My leading coefficient is +1, so I'm just not going to write anything at all. And then I will start writing my zeros. So x would be how I would write my 0 of 0. And then for this next one, I'll go ahead and write -2 as a factor. So I have to change the sign so that if I substitute in -2 plus 2 will give me that 0. And then I have my last one, x minus 3. Again, if I substitute in 3 minus 3 is 0. So this would be a possible polynomial for this graph. And we base that on the end behavior of our function and our x-intercepts.